Dive just a few dozen feet below the surface of a lake or ocean, and the light practically vanishes. Water molecules absorb electromagnetic waves so aggressively that relying on vision quickly becomes a luxury. Because water molecules are packed tightly together, kinetic energy transfers incredibly fast. Sound waves travel at roughly 1,500 meters per second underwater, nearly 4.8 times faster than they do in the air above. But this dense medium creates a paradox. Our human ears are trained to pay attention to sharp, loud noises, but what sounds deafening to us at the surface is often completely useless to a predator hunting in the dark. To understand how aquatic predators track their targets, we have to throw out our intuition about noise entirely and look at the strict physical rules of water. Consider a typical fishing crankbait. It contains internal metal beads designed to create sharp, high-frequency acoustic noise, sending rapid, tight ripples through the water column. Compare that to a large, unweighted swimbait. It makes no distinct sound, but its sheer physical bulk pushes a massive volume of water forward. To a human ear, the rattling crankbait is a screeching siren, while the swimbait is a ghost. Yet to an apex predator, that silent gliding piece of plastic acts as a far more powerful beacon. The reason comes down to physics. Water actively destroys certain types of kinetic energy, while letting others pass through. This process is known as acoustic attenuation. Water is viscous and heavy, and it acts as a thermodynamic filter, constantly draining energy from propagating sound waves. High-frequency sounds, like the rattle of a crankbait, pack thousands of wave cycles into a single second. Forcing dense water molecules to oscillate that rapidly creates extreme friction, which instantly converts the acoustic energy into heat. This logarithmic chart maps acoustic absorption against sound frequency. Notice how the data plots a steady increase across the spectrum. When the wave hits 10,000 Hz, absorption climbs exponentially. The water's friction penalty becomes so high the wave's amplitude is crushed. Because of this friction loss, those rapid acoustic waves are absorbed entirely within a matter of feet. The rattling noise is trapped close to the source, entirely cut off from the wider environment. The silent swimbait operates on completely different physics. The broad, slow pressure wave it generates requires a much longer wavelength, meaning the surrounding water molecules do not have to vibrate rapidly. Rather than a fast acoustic vibration that quickly decays, this low-frequency event acts as a continuous hydrodynamic flow, a physical block of water being displaced from one point to another. Without the severe friction penalty, this low-frequency pressure gradient bypasses the water's attenuation filter, holding its physical shape over incredible distances. But a signal traveling far is useless if the local biology cannot detect it. Predators waiting in the dark face a biological hurdle. Fish bodies are mostly water, making them acoustically transparent to pressure waves. Their traditional inner ears simply let these broad, low-frequency flows pass right through them. To solve this, aquatic hunters rely on an entirely separate sensory organ. It is called the lateral line system. Running down the fish's flank, this array of pores acts as a form of distant touch. As the displaced water hits the fish, the pressure difference physically bends the microscopic cilia housed inside the canals. These nerve clusters, known as neuromasts, are highly specialized. They are tuned perfectly to the 1 to 100 Hz spectrum, the exact low-frequency range that survives the ocean's acoustic filter. Aquatic evolution bypassed the limitations of traditional hearing entirely, turning the literal feeling of displaced water into the ultimate hunting tool. Out in the pitch blackness, the broad pressure wave from the gliding swimbait washes over the predator. The lateral line receives the flow. Instantly, the predator's brain maps the pressure gradient, calculating the distance, physical size, and velocity of the target, all without opening its eyes. The end result is a sudden, violent, and perfectly accurate strike, executed strictly from these hydrodynamic cues. These apex hunters operate in a sensory dimension that entirely ignores our definition of sound. Look back at those two lures. The rattling crankbait generates high-frequency noise that dies mere feet from its source. The silent swimbait generates a sprawling physical wave that acts as an unmistakable biological trigger. In a medium as heavy and unforgiving as water, survival depends entirely on moving mass, rather than making noise. Water is a strict thermodynamic filter, where high-frequency vibrations burn themselves out, leaving the deep, dark open for those who hunt by feeling the flow.